Thank you all for coming out. So this summer, as a part of the NSVP Simons program, I worked not at specifically any of the centers in this building, but I was working with the Simons Observatory, which is also funded by the Simons Foundation. And one of the member organizations, or one of the member institutes, is the University of Pennsylvania, which is helping to construct the telescope. Just some um, headwind there. So yeah, my project, I'm from the University of North Carolina at Chapel Hill, a rising junior, and I worked with Mark Devlin, Anna Kaufman, and Sayanish at University of Pennsylvania this summer. Oh, it's this one. Okay, so as I mentioned, the Simons Observatory, currently funded by the Simons Foundation, it's a cosmic microwave background experiment that is currently being built in the Chilean Atacama Desert, and it tends to map approximately 40% of the sky at arc-minute angular resolution. This is important because when determining characteristics of the cosmic microwave background, having a much smaller field of view allows you to see these anisotropies that are seen in the cosmic microwave background. And with that information and at the higher resolutions that the Simons Observatory will afford, we'll be able to determine or refine the cosmological parameters that are already determined from these anisotropies in the spectrum. And so one component of the Simons Observatory that will be taking on this task is the Large Aperture Telescope. And that part is currently under construction in Germany. That photo is as of this week, I believe, so quite literally under construction, and that's where it will be deployed to in Chile. And then the diagram showing where light would enter the telescope and reflecting off two mirrors before entering the receiver for showing the basic function of the telescope. And focusing more on that, the Large Aperture Telescope has two mirrors that are identified as a primary and the secondary mirror. And this design is called a cross-dragon optical design. This was optimized because, or this design was chosen because how optimal it would be for viewing large parts of the sky at also a very narrow field of view. And so something to remember when observing the cosmic microwave background is these mirror panels aren't meant for reflecting visible light. They're actually meant for reflecting microwaves. So that individual panel you see there looks a little dull, but that's intended. Nothing wrong with that one. And because the mirrors are approximately 6 meters across, it takes many individual panels to assemble the main mirrors for this telescope to work. And the surface of the mirror is defined by a fourth order polynomial equation. So in order for the telescope to work or for the receiver to receive, these panels must be properly aligned. And they're machined to an RMS of less than 9 microns. So the room for error is very little. The panels are very big, and there's very many of them. And that is part of the problem. When it comes to aligning the mirrors, each mirror is mounted to a backup structure and has 8 different adjusters. And the way to measure these panel surfaces is with metrology equipment, where points are measured across the surface of the mirror, and then alignment software that inputs this data will actually feed back saying that, oh, this panel needs to be adjusted at this many degrees, this adjuster knob needs to be turned this way, in order for it to fit that fourth order polynomial equation. And so the question is, with 146 total panels, it's going to be necessary to have an efficient and precise alignment. What is the best way to measure these panels in order to achieve this? And if it takes about an hour for each panel to be measured, that's nearly 146 hours of work that graduate students would have to do to align the mirrors. That translates to almost 6 straight days of work. And part of my job is, because I like the grad students so much, is to make their job easier. So how do we best measure this? And that was just one third day on the job experimental measurement pattern. So I learned over the course of this project what would be the best way to do that. And some of the metrology equipment I mentioned, there's a product called the Ferro Edge arm that was used in the laboratory. A different Ferro product will be used when it comes to actual alignment on site in Chile. But this tool has kind of like a little laser probe on it where you measure points that you want to measure, and the computer software will take these points and assemble them into a text file, which from there you can input into the calibration software. And so part of that calibration software that I mentioned, or the alignment software of the mirrors, the workflow that would happen without my contribution is that a measurement would be made and it would be fed into the alignment software, where then the input of the text measurements would output adjustments to be made to the adjusters, the overall RMS value for the surface, and the power spectrum graph showing roughly where adjustments can be made on the panel. And in order to determine what was the best way to measure this, the new algorithm that was devised, that I helped devise, was taking a default measurement text file, which had approximately 235 points, which again, 235 data points of clicking a green button on a machine would take a decent amount of time. Part of the motivation, again, how can we do the same with less? So this algorithm takes that default measurement and it changes, it modifies them to different parameters, such as, what if we only looked at measurement points around the adjusters? What if we only looked at measurement points away from adjusters? What if we just had an arbitrary grid? Different measurement scenarios to determine, can we achieve the same result? And part of that software also spits out a plot for showing every black dot is a measurement made here, so that's a lot of measurements. Can we do more with, can we do the same with less? And so these are more outputs and scenarios for that algorithm for measuring. So these are more spatial graphs. This one was saying if we only allowed a certain density around the adjusters. This one was only so few away from the adjusters. And this one is more or less an arbitrary grid. And here's a reduction that we're able to see when we had 235 measurement points. The RMS that it returned was 7 microns. And even reducing it by nearly a fifth to 69 measurement points, we were still able to achieve 6 microns for our RMS value. The graphs of the power spectrums of these adjustments, that's something that the software calculates and feeds back. But for the sake of ensuring that the mirrors are fitted correctly, this final RMS value is what's most important. And so that if every individual panel is able to be under 9 microns, then we're able to go forward confidently saying that the whole mirror has achieved the fit. And so yeah, a reduction of almost, reducing it by a fifth is a fifth as much time to measure every panel. And that instantly takes it from 6 days to maybe less than a day to get all this done. And again, something else worth noting on these charts are, again, like the primary scenarios that we're looking forward to is if it was just the adjusters that were the most reflective of the actual RMS value, or if it was necessary to measure every point on the surface. And so the current status of that is, so far, over 40 measurement different test patterns were generated and tested. And like I said, the arbitrary grid will remove every nth point. The adjusters will only allow the ones that are close, and the ones that are far away only allows the ones outside a certain radius. And this is the current graph that, by measuring the RMS values for every one of those test measurement scenarios, we're able to see that as I reduce the number of measurement points, are we still able to achieve like roughly around 7 microns? And it seems that, you know, out here, we're seeing like 100 measurement points, which is already starting off half as many as we were initially given. But we can still do less. So looking in this area of now you start to get into 40, 30, 20 measurement points. It goes haywire once it goes below 20 so far for most of these scenarios. But the next step in this project is refining the search to say what scenarios were best at this, what looks promising to be between 50 and 20 data points. So from there, that information will be used by the graduate students to make those 146 measurements of the panels for the observatory to work correctly. And just some acknowledgements. I'd like to foremost thank the NSPP Scholars Program, Casey and also Saran and Shannon for making this possible, the observatory, the National Society of Black Physicists, and those at UPenn that helped me put this all together. And that is me at the labs at UPenn in front of the receiver for the Large Aperture Telescope. So the whole thing is pretty big and really cool. So
All right. So I'm actually again going to start with a comment. At the end of lunch, I was talking to David Spergel, and he told me that something that he's learned in life is that the best thing money can buy you is time. And I think what he really meant is the best thing that an NSBP scholar can buy you is time. At least Nathnael has bought that for the Penn team. Okay, sorry. So questions for Natu. So when you go, I have a question. I mean, I have a million actually, but I'll just ask one.
Go right ahead.
So you're talking about making measurements on an individual panel,
Correct.
right? But ultimately, these same measurements would need to be made on all of the panels,
Correct. Yeah.
and after they're installed. Is that right?
Yeah, when it goes to be installed, when deployment happens in Chile this coming year, each panel on the backup adjuster structure will need to be measured. And from there, those adjusters get adjusted to make sure that the fit is made. So yeah, this will need to happen for every panel.
Yeah, Zach.
Cool. Thanks so much for this. This has been really cool. So for the power spectra that you were showing, can you say a little bit more about what those actually tell you or how you're actually getting them, and then how you're converting that to a root mean square value?
Right. I believe that these power spectral distributions show actually like, because even if you see the one with fewer measurement points, there's inherently going to be more noise because there's less signal or less information to be plotted there. So even though it appears noisier, the power spectral distribution and the location of it. So I should probably talk about the axes. The axes being the Y is the RMS values that are read between different measurement points. And then the scale showing that the distances between each measurement point, where are points most needed to be adjusted. So a higher RMS value spotted at the 70 centimeter scale would say that at that scale, that's where adjustments most need to be made. But it's optimal to have scales at a lower at a lower scale. That's not really physically possible. We can't change something on like the 2 centimeter scale for a 70 centimeter panel. That is something that can be, doesn't affect the overall fit, but is just showing, given the information it was given, the test points, that's what it's finding. But that also isn't reflective of the whole surface. So that's why this is informative, but the final value is what helps us to determine the full surface.
Is the final value an average or a median, or how are you?
I believe, if I remember correctly, I think it's the integrated value.
Okay, cool. Thanks.
Okay, so I think we're out of time, so I think we should wrap up. Let's thank Natu one more time.